Thank you. And so let me first start by thanking the organizer for this very nice invitation. First, a disclaimer, if you want. I'm a theoretical physicist, so I will try to flash over some recent work we have been doing about topics more in the field of quantum simulations and quantum computation. I know the audience is very broad and wide for interest and background, so I hope I tried to be as explicative as possible in all what I'm doing. So I apologize for the people who already know this stuff, but I think it's nice that everybody can get some message out of it. So, you know, I think you all know that this idea of quantum simulation and quantum computation actually dates back to a famous speech and then a paper by Richard Feynman back in 1982 to what was the first conference on physics and computation. And he was in his, let's say, really deep insights that sometimes, actually very often he had. He was proposing the fact that actually a computer should be quantum. Okay, why? Because the universe in reality is quantum, and so if you really want to talk, as he said, about the possibility that there is an exact simulation, then the computer should work exactly as nature does, and so it should be quantum. So that was really very first time in which people thought about that. But this, as you know, it's an old story, so why talking about that now? And the whole idea is that actually we now do have some technologies that can support us in doing quantum simulation and quantum computation. Actually, we do not have a single technology that is able to do so. We have different physical platforms in which we can try to do quantum simulations and computation. And here I'm just flashing through the most famous ones. Even if at the very end of the talk I will concentrate on the last one, which maybe it's less known to the wide community. This is a technology which is based about neutral Rydberg atoms. But just because we had the possibility to run an experiment in Pascal company with their computer. In the United States, the biggest company that is developing this kind of technology is QEra, but we've heard, of course, of other technologies like Google and others that are using different platforms. Up to now, each of them has advantages and drawbacks, and so we really do not know yet if there will be a single technology that will overcome all the others. But so as a physicist, we are trying to explore all the different possibilities. Okay, let me talk a little bit about this NISQ era that somebody also mentioned 2 days ago. Preskill in 2018 came out with this definition, NISQ, which stands for Noise Intermediate Scale Quantum Computers, and which is somehow connected to two things: the number of physical qubits we are available, and the error rate. Okay, so how noisy or how exact can be our computation. And he said we are now in the NISQ era, and it will take about 5 years to start to be in what we call the fault-tolerant quantum computing era. Okay, so we are now in 2024, so we are essentially right here at the time. The question is, are we in the NISQ era still, or can we really think about going towards fault-tolerant quantum computation? I leave that open. I think there are different opinions, but I really think that the last developments, the technologies are really bringing us very fast toward this fault-tolerant quantum computation. So maybe our research will very soon be directed in that direction. Still, what I'm going actually to talk about today is more connected to this NISQ era, because I'm trying to work on this hybrid algorithm that somehow are trying to take into consideration the fact that we have not so powerful computers and computers that are still quite noisy, and we don't have error correction codes that can work on that. Okay, so the reason why, let's say, I'm interested as a theoretical physics in this field is actually because it is it brings together different areas of physics, at least, which include high energy and condensed matter physics, statistical models, that is actually the area from which I come from, together with a lot of synthetic platforms, more experimentally, in which we can try to make experiment. Of course, behind that, there is a lot of mathematical structures that come from the mathematical structure of quantum physics that actually govern all this stuff, and is, as we heard in these days, something that is really very interesting and beautiful to study. The reason why we are interested is that actually the new platforms that we have at hand now, that can be superconducting, spin, cold atoms, ions, whatever, are actually very versatile, so that we can think of or doing simulations for a lot of different problems. People nowadays talk a lot about chemistry, okay, that can be done on quantum computers, more general condensed matter models in order to study material science. There is a lot to do about statistical mechanics and critical phenomena, quantum phase transition, and so on, and also a lot of things to say about fundamental interaction. So, for example, I'll give you two examples about particle physics, okay, but there are also other examples about gravity. And the idea is that actually quantum simulation can allow us to go beyond our standard analytical techniques that are available. So we can study non-perturbative effects as well as real-time dynamics, and that can help us to understand better novel effects and new situations that go beyond the standard techniques of calculation that we have. But also, and we will concentrate a lot on that, all these quantum simulations and computation can actually give us new ways to study hard or complex as you want, classical problems, such as combinatorial problems of graphs, for example. I'll be talking about that in the last part of the talk. Okay, so actually, let me talk first about what usually in our community we call a quantum-inspired computation, okay, which has to do really with tensor networks, which is the topic of this conference. So we know that tensor networks are very powerful. We have heard of a lot of applications in these days that go from the study of quantum eddy Hamiltonians, out of equilibrium physics, their application to machine learning, to simulation of quantum circuits. So really, tensor networks is, in all its variants, has a lot of applications. And the reason why it is so is that actually it's very rooted in the physics and mathematics of the problems we want to study. And that ability to exploit understanding what's going behind the model can give us very powerful computational tools to be applied to a large variety of problems. Just to give you an example, I want to flash on a paper we had a few years ago about studying a model which is called the Dan-Schwinger model in one dimension. And just, I don't want to discuss the formulas. I just put them for completeness. But let me just to give you an idea why this model is interesting. It's actually the simplest version of the electromagnetism that we can do. Okay, so the electromagnetism in one dimension. And technically, it's therefore called the 1+1 quantum electrodiagram, and it is a gauge theory because we have a gauge symmetry, which is implemented by a Gauss law with an abelian group like U1. Okay, if we want to do a quantum computation about that, we have to discretize it. So what we did was to discretize this model on a lattice, first of all, in one-dimensional lattice, like here. But also we have to discretize the U1 group, and that's why we end up in what we call the Dan-Schwinger model in one dimension. I'm not going into the details. Let me just say that this model is interesting, despite being, if you want, a toy model. It is interesting because it displays the phase transition for a value of the mass of the particle, of the charged particle. I don't see here, okay, which is about, actually, I forgot the minus 0.3, as was known to Schwinger many years ago. and from what is called a deconfined and a confined phase. And that's something very interesting because it's something that does not happen in electromagnetism in 3 dimensions. But yes.
Just a little confused.
Sure.
So what are you given and what are you trying to find here?
Okay, this is a model, okay? What I'm going to show you that I can do real-time dynamics of this one, so study out-of-equilibrium properties of this model using quantum-inspired methods, okay?
So the model has some dynamics and you're going to discretize and show
Yes, so this is my Hamiltonian, okay? I have a system which is made up of fermions, which are these psi that are put on vertices, okay? And on the links, I have the electric field here, which is has a symmetry which is discretized from U1 to Zn.
So just a sanity check. So you're given psi at time 0, and then you're going to get
look for the evolution. Okay. I'm going.
But you're going to show us how you're going to do that, right?
In a moment.
Okay, because the picture doesn't tell me that.
No, this is just the model. This is describing the Hamiltonian that we are using. The degrees of freedom, if you want. This is describing the degrees of freedom that we have. Okay? And the reason why we're interested in this simple model is actually that a much more complicated problem, which is quantum chromodynamics, so quarks, in elementary physics do have the same kind of phenomena of confinement. So we are interested to study so. And I'm going to show you what are the effects of this confinement. I'm going to describe you the physics behind it. And what we did in this idea of quantum inspired, so using a numerical simulation which is based on time-dependent density metrics normalization group, okay? I'm just choosing Z3 here for to be as an example, but one can do it for Zn in general. We are studying a problem that is called spontaneous production. You know that in quantum field theory, you can start from the vacuum where you don't have any charge, okay? But charges are generated spontaneously from the vacuum because I can create particles and antiparticles, okay? These processes are allowed in quantum field theory. And so what we do is exactly we want to study that. So we start from the vacuum, what physicists call the Dirac vacuum. There's no particles, which is actually the ground state of this Hamiltonian for large M. One can show it, okay? So that's the state we start from. And then we just evolve it. So we take e to the I th, where h is the Hamiltonian here, and we let it evolve in time, okay? So you calculate how the starting partition function, which is a vacuum, no charges, evolves in time, okay? And here, what I'm plotting here is the average particle density. So what you see, we start from 0 because originally we don't have time. And using tensor networks, if you want time-dependent density elimination group algorithm, you start seeing that particles are created out of vacuum, okay? And then there are all these oscillations going on with time, okay? And this, so this is what you can predict for using time-dependent density metrics group, so really quantum evolution of our system. And what I would like to show you that in 2016, this experiment has actually been done with atomic atoms, okay, with a very small number of atoms that were just 4 particles, okay? But so it was a vacuum of 4 particles. But the green curve is the theory that comes from here, and you see the 2 colors are experimental data, and they fit very well, okay? So this can also be simulated in experiments. I just would like to show you why these oscillations, okay, are important from a physical point of view. Actually, these oscillations start to occur when the mass is close to 0, okay? And this is what happens, for example, in this picture. What I'm looking here are the correlation functions, okay? And we start with nothing, vacuum, so there's nothing. And as we go on, we see that the correlations start to grow, okay? So we have this red scale appearing, not black. And what we see that the correlation actually spread along a light cone, something that has been mentioned also in previous days. So the correlation between particle and antiparticle that are produced here. So there will be a particle-antiparticle produced here, and they move, and the correlation among them spread in space according to the laws of electrodynamics, and we expect a light cone. But actually, when we go with very high masses, so we enter a region in which the interaction is very strong among particle and antiparticle, what happens is that this picture that is what one can naively expect, actually it gets completely suppressed. And we see that the correlation spread for a while, then the two particles recombine. So again, here I have vacuum, and then they are particle and antiparticle produce again, and they keep going. And this is the reason of these oscillations. And this is a phenomenon that is very interesting because what this is showing you that you start from some state, you want to see at large time, for example, to which state it will tend to, will thermalized, okay? And here it's very clear what happens. Instead, here we have this periodic oscillation that will not bring you to any specific state in particular. So somehow, I mean, talking from statistical mechanics point of view, this will be a sort of lack of ergodicity in your system. So that's a problem which is very interesting to study, okay?
I have a question. So both the phenomena are considered like quantum phenomena.
These are purely quantum phenomena because the reason why that happens is that there is a very strong interaction, and without interference of the wave function, we will never see things of that kind.
So what is this exactly a picture of? Is this some simulation?
This is simulation using the tensor networks techniques, okay? So I start from the vacuum.
So you have 4 pictures. The first one is simulations or?
No, all of them are simulations, okay? You have time in the horizontal axis. So you see the initial, this is a lattice of 80 sites, for example. So here I have my lattice, okay? Here I have time. Here everything is black because I have nothing. So the black corresponds to nothing. And here I start from 0 because it's the average particle density. I have no particles, okay?
I was just asking you this. And are you going to sort of show us under the hood the exact mathematics you're doing to get these pictures?
This is standard density matrix renormalization. I mean, tensor network, I mean, the numerical situation. So I start from the vacuum, that's my initial wave function, and I numerically evolve it with e to the ith, which is this one, okay? And I just look at different times my wave function, or if you want to, some observables.
There's no tensors on that slide. That's the previous.
Okay.
Okay.
So here, what I'm showing you is the outcome of the simulation, looking at some observable. In order to understand what's going on, we have to look at observables, right? So here we are looking at average particle density that is telling us how many particles we have as time evolves. So we started from 0, we saw this production of particles, which is periodic, and we look also at correlations. Okay, I just keep this one. And so, of course, the idea is that this kind of quantum-inspired calculation, in which I start from a wave function, I have a Hamiltonian, I calculate numerical using tensor networks, for example, the real-time dynamics of what's going on, okay, can, of course, be brought almost with the same ideas to what we call a digital quantum simulator, okay? And what we have to do in what we call a digital quantum simulator, of course, we should encode our degrees of freedom in the quantum states, so as a suitable number of qubits, okay? Then we have a quantum evolution, which is given by the exponential of minus ith, whatever it is the Hamiltonian of our problem. And what we have to do is transform this evolution into gates, okay, using the fact that quantum computation is universal, so we can split any unitary evolution in terms of elementary gates, okay, which usually makes use of poly-Hamiltonians, poly matrices, and then at the very end, we have a piece of the circuit that will make measurements of observable correlation, whatever one wants, okay? So that is really mimicking at the quantum level what we have seen, what we can do with classical computers. What instead I would like to discuss you today is another, let's say, paradigm, which is what we call analog quantum simulators, which somehow it's very similar because we still do have to encode our degrees of freedom in a Hilbert space, so we should represent our degrees of freedom as qubits, okay? We still have a quantum evolution, and then after we have done the quantum evolution, we will take a measurement to find the mean values of observables or correlation functions. But the main difference, which is very subtle, and say the borders are not very clear, but let me say it in this way, is that here we have a Hamiltonian which is fixed by the platform in which we work, okay? So our platform will actually be able to deal with only a certain kind of Hamiltonians, okay? And the freedom I have to choose this Hamiltonian is in the fact that the Hamiltonian can be time-dependent, and I can control this Hamiltonian through a small number of time-dependent parameters. I'll give you an example in a short time, okay?
Could you go back to the previous?
Well, I mean, the idea is that what you do, maybe I can write on the blackboard, okay? When you do a digital, you think that you have a digital, you think that you have a Hamiltonian, which means a self-adjoint operator, okay? And that means that when you take the exponential, this is a unitary, okay? And then there is a famous theorem in quantum computation that is telling you that any unitary can be approximated with the precision you like by using single qubit
Yeah, in math it's called
plus some entanglement gate that can be a C0 or whatever you like, okay? That is needed to make entanglement, okay? So what you do is that any unitary should be split in a series of gates of single qubit or C0s, okay? And that is a universal kind of stuff that you can do. And in principle, maybe it's not efficient, but in principle, you can do any Hamiltonian in this way, okay? So that was
mathematics, that's called carton du donatio.
okay. Then in this idea of analog instead, you are given a class of Hamiltonian that your physical situation can actually deal with, okay? So I can evolve my experimental setup only with some kind of Hamiltonians. And the only control I have is in a number of parameters that can be time-dependent that appear in the Hamiltonian. So in this sense, it is not universal, okay? It will be able to, let's say, produce maybe a large class of problems, but in principle, it's not universal.
So up top, you have H that doesn't depend on T.
Yes, the whole time dependence is in front. Here will be inside. No, it will be inside the Hamiltonian, as you will see.
So H's are completely different, right?
Oh.
The top is the Hamiltonian you want to simulate. The one on the bottom is what replaces your gates, right?
Yes. But the idea that then if my problem, the problem I want to simulate, adapts somehow to this kind of Hamiltonian that my system is able to deal with.
In the algebraic perspective, you have a set of generators for some dynamics, and you try to use it to generate some dynamics.
Okay.
But it might not generate the full dynamic.
Actually, I mean, the difference is quite, there was another question, maybe I can take that.
I think you answered.
Okay.
You really think about the few, when you say a few parameters, you mean really mean
two, it will be two, okay?
Not like a
Now, let me say that actually the difference is quite subtle if you really think better, because when you create these gates, what you do is exactly the same, okay? Because you go to a microscopic level, you have a microscopic Hamiltonian, and you are controlling that macroscopic Hamiltonian to do a single gate.
But it's not like
But the big picture is different, okay?
it's not like 1,000
Okay.
values of
Yes. So, and the idea is that I will act with this Hamiltonian on the whole system. I'm not splitting it into single gates, okay? That is.
And just a dumber question. Why the choice of words analog and digital?
Because that has to do with the fact that this kind of picture will be good for some class of problems that somehow can be reproduced through this specific Hamiltonian. And it's actually also what happened in, let's say, classical computer in the early 40s and 50s, in which we had a digital way, which is indeed what we have today in any device that we have in our pockets, okay? But also, we had analog classical computers that were specific purpose computers that were made to solve Let me just give you an example. If you want to solve a given class of differential equation, I can construct an electromagnetic circuit, because electromagnetic circuit is providing for us a realization of, okay, that's what I have in mind, okay?
It's probably not a very good wording, but people use it.
No, but now I understand. I'm a mathematician. As long as you tell me the definition, it's an unfortunate choice of nomenclature. I'm okay because I know the definition. So this is fine. I'm happy now.
Okay. So, given so. Okay, and in this context is where we would like to study what we call hybrid variational algorithm for optimization problems. Let me explain why, okay? This is a context, so this is analog context, the context we want to study this. First of all, let me tell you a couple of words about why optimization problems. This is actually easy because we know that many problems of interest can be cast as an optimization problem. Actually, as a physicist, and I think also as a mathematicians, we are very happy if you can cast any problem in a variational way, okay? Usually we are very happy if you're able to do so. We know a lot of classical combinatorial problems that can be cast in such a way, the traveling salesman's problem, the MIC problem on a graph that I'm going to discuss in a moment, and many others. But also many quantum mechanical problems are actually of this kind, because if we want to find the ground state of Hamiltonian, what we want to minimize is the energy, okay? So we have a function that in this language we call a cost function that will describe our problem, and the solution of our problem is the global minimum of this function. All these kind of problems can be cast in this way, okay? So we have a function that we call the cost function, and we want to find the solution, the minimum of this function. Usually what we do, the problem is too complicated, the space in which we work is a very large dimension, so many times we use some variational ansatz to solve this problem. So we introduce a given number of parameters to explore, let's say, to describe the space of solutions, and we try to find what are the best parameters that give us the solution of our problem. Okay, this is what I have in mind. And why hybrid protocols? And what do we mean by hybrid protocols? We have in mind that the problem that we want to solve in general are hard, okay? This is true at least for two reasons. The first reason that usually the resources that we need to solve this problem scale exponentially with the system size. This is for sure true in any quantum system, but it's also true in all the combinatorial classical problems I was talking about. And this is actually not feasible now in the NISQ era, because this problem requires both a large number of qubits and usually a very deep circuit, a very long circuit, and so there is noise that is preventing us to do anything, okay? There are many hybrid protocols. I'm going to concentrate on this one that is called QAOA, which stands for Quantum Approximation Optimization Algorithm. And the idea here is that our input state is actually manipulated with a quantum circuit with a set of parameters. So we will choose, if you want, a set of parameters in our Hamiltonian, and that will allow us to evolve our state and move in the Hilbert space. And then we calculate the final wave function, and we will calculate the cost function out of the final state, and then we will go through a classical computer that will try to optimize these parameters, and we go in a loop until we reach the necessary precision, okay? This is something that has been around for quite a long time. Let me just give you a better explanation of this protocol, that therefore what it does. The idea is that you use a quantum computer to prepare a ground state, which is usually the hard part, okay, of the problem. And then you resort to a classical computer to find the optimal solution. That's the whole idea of these hybrid protocols. Let me go back to the QA and tell you a little more what we are doing. So we start by defining what is our cost function, and that means that we have a problem with some degrees of freedom, and we have to embed our degrees of freedom in the Hilbert space with the suitable number of qubits, of course. And then we have to encode to find a Hamiltonian, a quantum Hamiltonian H, such that the solution corresponds to the ground state of such Hamiltonian, and the average of our Hamiltonian will become our cost function. So that's the first step that we have to do. So translate our problem into a Hilbert space and a Hamiltonian in such a way that the cost function becomes the expectation value of our Hamiltonian. That's the first step, which is out of this picture, okay? It's here, okay? Then we prepare, let's go to the quantum circuit part. We prepare our state in some initial state, okay? That also might be a non-trivial thing to do, because if the states you need to start with is hard, that's another story, but I'm not going to enter. And then we prepare a parameterized quantum circuit. So we'll do some evolution here, fixing this time with some parameters, okay? I'm going to show you what we are going to do. And that will give us the evolution of the state, okay? We start from the initial state, we evolve it with our parameterized quantum circuit, having chosen some thetas, some values of the parameters theta. Then at the very end, we have to do a measurement, okay? And you have to take, so maybe you have to change basis, whatever, but at the very end, we calculated the average value of the Hamiltonian on the state psi of theta that we have constructed with our parameterized quantum circuit, and that is our cost function for the values of the parameter theta that we have just used in the quantum circuit. And you take in this average, we plug it into a classical computer now, okay, which will use your preferred algorithm to optimize it, okay? There are many algorithms that can be used here. Actually, we'll discuss some of them in a moment, because our work has actually been concentrated on the fact to use some algorithm that is particularly suited for the kind of problems, this quantum problem that we are dealing with. Because as I will try to make you understand, the way we use this classical part, which seems very simple, is actually very important to make something that is efficient. Okay, and then we repeat that, okay? I was trying to think. Okay, I think it depends on the time I have. Maybe I come back to that because I would like to concentrate on the last part. Okay, so all these steps that I've just mentioned to you have a lot of theoretical issues behind it that one has to keep under control. For example, the way we embed our degrees of freedom in the Hilbert space, the choice of the Hamiltonian, all these questions, of course, do not have a unique answer, and so they're very important to deal with. There are convergence theorems that you want to understand if really your loops do converge to the final solutions or not. And so there are a lot of work done in this direction. And going towards quantum computation instead, one should be aware that if you really want to take into consideration all aspects, still this protocol can become also very resource demanding. And in particular, if you work on a NISQ device, you should be careful that memory resources are still limited, okay? And that holds true both from a quantitative point of view, because you have a small number of qubits, but also because connections among qubits are not all possible, okay? We've seen, for example, for the IBM device that it has only some very specific connections. So some operations are easy to be done, others are very difficult to be done, and that can be very demanding. Also, for the same reason, if you want, the depth of the circuit to make the evolution you like with the generic kind of parameters can become very long. You can have a very deep circuit, and that is a problem in a NISQ device. Also, another thing that usually is quite overlooked is the fact that in order to calculate, okay, I have to go back, okay, several times. Where was it? In order to calculate this expectation value, okay, if I know analytically the wave function, that's something very easy. But if I want to do it with a measurement in a quantum computer, I do not measure directly the expectation value. Each measurement will give me one possible eigenvalues with a given probability. So I have to repeat that many, many, many times in order to have a suitable number of points and to be able to calculate the statistical average, okay? So this also is something that can become very demanding, okay? And also, we have to do this loop. So while we are doing the classical optimization, we should better keep our quantum computer coherent so that you can repeat the loop, okay? So there's, say, something that has to be checked. And of course, we also would like to understand if you can keep under control the noise, okay, of our quantum machine, and you can suppress it somehow. So there's really a lot of things that we want to take into consideration. So in order to test that, we decided to work on a classical problem, which is the MIS problem in a graph that I'm going to define in a moment. And as a classical optimization procedure, so the classical part of this hybrid protocol, we proposed to use what you call a Bayesian adaptive technique that I'm going to explain you in a moment and why we decided to do so. And then we had the possibility to solve this kind of problem in a real platform, which is the Pascal neutral atom computer. And I'm going to tell you at the very end some results that we got last week on that, okay? So what is the problem we have in mind? We have a graph. Here I'm just giving you a very simple example. And the max independent set problem consists of finding the larger set of nodes which are not adjacent one from the others, okay? So the solution of this one can be cast in a binary string because what you do is to give a 0, 1 to each node, okay? So my variables are binaries. And the idea that no two ones should be close one to the other, okay? That will tell you that I'm splitting this graph into sets, the one with the 0 and the one with the 1s, and we will see that is a solution. Okay, so the solution for this simple graph, for example, is given here. Okay, so that can be very easily cast in a variational way because this cost function that you read here with the binary variables 0, 1 can indeed give us the solution because, as you can see, I'm just counting with the first part how many ones I have in my graph. And then I'm giving a penalty with this term whenever two nearby two nodes that are connected by a link have both a 1. Okay, so it's sort of Lagrange multiplier kind of situation.
Can you remind me of the classical complexity of this problem?
It's NP.
Is it NP complete?
Yes. It should be NP complete if I don't, okay. And this is one of the, actually, then if you go to a dual graph, this gets transformed into the max cut problem. So actually solving the max cut problem, the MIS problem is essentially the same, okay. This can be easily be recast also using not binary variables, 0, 1s, but let's say spin variables, plus or minus 1, by simply doing these transformations, okay? And once you have cast your problem with classical spin variables, plus or minus 1, what you do is take your classical variable, make it quantum, okay? So we substitute the z variable with the Pauli z matrix, okay? So the quantum Hamiltonian can be very easily obtained. You just do all this transformation, and you get this very final piece, which just counts how many plus or minus you have on your sides, your spins, plus an interaction term with a penalty, which is suppressing the fact that you have two ones in adjacent positions. So that's the problem, okay? Why choosing a Rydberg atom platform, okay, neutral atom platform? This is something that I just tell you very easily. There's some physics behind it. So this platform uses Rydberg atoms. Rydberg atoms are the first column of the periodic table where also hydrogen is, and in particular the Pascal company is using rubidium atom, okay? And the idea is that these are very stable atoms, so they're very good for quantum, as a quantum resource that can be controlled very easily with lasers, okay? So that's the technology we're using. And there is one characteristic of this technology that helps a lot this kind of problem, which is what is called the let me say, these situations are very versatile because you can actually move atoms in space using these lasers and put them in different positions. So they can create different geometrical arrangements of these atoms. And for example, for them, it's very, very easy to create triangular lattices like these ones, okay? And you can choose where to put your atoms, Okay, you load the atoms in your systems the way you want. Okay, so this is something that for graphs can help a lot because you really put your qubit in the right position, and you have the connectivity of the graph already. Okay, of course that cannot be done for any kind of graph. Okay, because some graphs cannot be embedded in R3 without self-intersection, so that kind. And then there are other techniques to take care of that. Okay.
So what is this going to tell us? What are we? So we're feeding it in this data, and what is it?
No. This is the experimental platform that we are going to use at the very end to do the quantum computation, real quantum computation, okay? And the reason why we chose that one is that it has two characteristics that is helping us. One is that we can actually simulate a large class of graphs in a nice way, because you can put atoms wherever you want. And the second reason is that there is one phenomenon that I'm going to discuss, which is called the Rydberg blockade, that avoids the two atoms that are nearby here are in the 1-1 status. So there is an interaction in the Hamiltonian that is avoiding that, okay, by construction.
Is it computationally efficient, given a graph, to figure out if I can find an arrangement of Rydberg atoms which reproduces the correct interaction?
I don't think so. No. You're a mathematician, you tell me that.
Sounds like a fun problem.
That's a very interesting problem.
Well, you tell me the constraints, then okay. But I guess it's a planar arrangement, right?
No, they can do also 3D arrangements. Okay, it's not so easy, but they can also do 3D. I think there are a lot of theorems in that direction. Okay, that of course there are a lot of theorems telling if your graph is planar, right? That is.
But it's more. No, they need to be at a specific distance, so you get the correct direction.
Yes.
So it's
In fact, some graphs are not easy.
Or
no, I mean in principle. What you get that if they are not exactly the same distance, that you should put some other penalty terms in the Hamiltonian to take care of that. So or what you can do is actually to add some degrees of freedom more, and that you keep in the force by some other penalty terms to stay in the ground state, so will not take. So there are a lot of tricks that one can think to enlarge the class of graph. Okay. So this is Hamiltonian, okay? This analog Hamiltonian that this computer, this specific platform is able to use, okay? So sigma x is a Pauli matrix acting on each vertex, j is a vertex, and then there is also this matrix nj, which is just 1 plus sigma z over 2. So you see this matrix nj is eigenvalue 0 and 1, depending if your qubit is in 0 or 1, okay? So this, and the two parameters I can control with time are exactly the two coefficients which are in front of this term. So there are two parameters in this case. This is something that in quantum optics is very known. This is a Hamiltonian that is used a lot to control atoms. So something that we have a real, very powerful techniques to control this Hamiltonian. This, for example, is called the Rabi frequencies. It's called the detuning, but it's not important. And then you have this interaction term. So atoms are interacting in couples, okay, with an interaction, as you can see, scales with the inverse of the 6th power of the distance. So the idea is that essentially this interaction is effective only if they are nearby. If you are larger distances, it's essentially 0, okay? And this is exactly what, since this coefficient C6 is positive, is avoiding for you is giving you a strong penalty to the situation in which both are in the one state, okay? So this object here, which is what gives origin to what is called in quantum optics Rydberg blockade, actually gives you a very high penalty, which is constructed inherently inside the quantum system that I'm using. That is, let's say, somehow projecting out the subspace in which both sides are in the in the excited state. Okay, so this is really helping a lot to the computation. Okay, because it's already projecting out from your Hilbert space in an efficient way those states that you do not want. So in practice, you're working in a smaller subspace. Okay, and this is just an example of how you can control these two parameters in time. So you can use omega of t, for example, in this example, which is always on and the constant function, whereas this delta of t is some stepwise function, so it's on in some periods and not on in other periods. Okay? It's something that you can do. And there are many shapes, many things that already you can use to control that. Okay? So this will be, okay, and the parameters we are using, so the variational parameters that we are using are essentially the time, okay, that are here, okay? So we turn on these two functions with step-like function for different times. So there will be θ1 here, θ2 there, θ3 there, and so on. And so that will give us a set of parameters with which we construct the quantum evolution of our original state, okay? Okay, I want to say something about the Bayesian optimization that we use to describe the classical parts, and then I will put them together. And just I would like to tell you why we decided to use a technique which comes from, I mean, is very quite common in statistics, let's say. This is actually a global strategy, global optimization strategies that allows to find the minimum of a function that is in general expensive to evaluate, okay? I can answer your question later if you want. I'm not entering all the details. This makes use of a prior statistical distribution that for us is a Gaussian. So you're using Gaussian processes to update a posterior distribution. And what is this distribution is telling us, is giving us from statistical inference, what is the next point in which we want to calculate our cost function, okay? In principle, you can use some global method so that we start from some point, then we start sampling our space of parameters in some way, or you can use a gradient descent method to go toward the minimum. You can choose the one you want. This is a statistical inference method that allows you to choose what are the best points in order to go and calculate your cost function, because those are the points in which you have less information, okay? So you choose the new points that will be able to give you the maximum information possible to understand the shape of your cost function, okay? Why we are doing so? We are using exactly this technique. There are several reasons, because this can avoid a problem that is actually ubiquitous in all these quantum problems, the fact that the shape of your cost function is actually affected by this problem that is called the Barren plateau, something that is very well known in literature. The idea is that as soon as you go over a few number of qubits, your cost function actually is almost flat. So any local method that works with the gradient descent will not work because your gradient is essentially zero. So you spend a lot of time in flat areas. And you can get stuck also in local minima, okay? And this is a global method that will avoid that. The other thing that it's being a statistical kind of stuff, it can reduce the number of points that you need to know in order to proceed, so it's faster, so the convergence is faster, and that will reduce both the number of time you evaluated the cost function and also the number of measurements you have to do. And as you will see in a plot in the next slide, it is quite resilient to what we call a white noise, okay? We did that. I'm going to tell you what it is. Okay, so let me say what we have done. Okay, we have tried first, since we have chosen an algorithm with all the details I told you before, let's try to simulate in a classical computer, thinking that you don't have noise, we don't have any kind of error, okay? And this first slide, which is very complicated, just let me concentrate here, is showing you what are the results of our protocol if you're using different classical optimizer. Our is this blue one, okay? And then there are other typical optimizers like dual annealing, Bayesian hopping, differential evolution, so different techniques, okay, that can be used for the classical part. And as you can see, the depth P is how many times you repeat our procedure. Is a Bayesian inference is actually much faster, okay? So that's the reason why you're using that. 2 minutes, okay. Okay, and as I told you, that will allow us also to reduce the number of shots. And it's also very resilient to, if you think that our theta parameters that we put in the evolution are actually can also have a Gaussian error, okay? So they're not chosen precisely by our quantum computers, but they are chosen with some random Gaussian distribution, okay? So this statistical inference method allows us some robustness with respect to these statistical and white noise errors. Then what we did was to do a simulation on using Pulsar, which is the Pascal package similar to Qiskit for IBM, okay, that allows us to include their noise model, okay. So these are the convergence, looking at different parameters. I can go back to that if there are questions. Introducing noise. So from there, for example, we saw that we does indeed go to very high approximation ratio for the energies. R is approximation energy. But even if you have noise, theoretically, and then we did it, okay? Then we did it, we ran it 2 weeks ago on their computer, which is called Fresnel, okay? As you see, it's a small computer, it's not very big, and it works at room temperature, so it has some advantages, okay? And these are indeed exact experimental results on some specific values of theta, just that helped us to calibrate whatever we were doing. And these are our final results. I'm just showing to you these ones. So we were able to went up to a graph with 15 nodes, and we repeated our loops 5 times. And that corresponds to the fact that we made 50,000 shots, meaning that we ran the circuit 50,000 times, okay, in order to get all the data, okay? And that took about 12 hours, just to tell you how long it takes. And these are the simulations that we did, okay? How should the energy, for example, should converge to the correct one. So this graph should go to 0. And these are the experiments on the real computer. And as you can see, the things are quite working, okay? We are still analyzing the data, so I cannot tell you much more than that. But it seems indeed that at least with these sizes, we would like to go to much higher sizes, but the company didn't give us enough hours to do so, so we couldn't do it. I mean, still, this has 15 qubits, so the Hilbert space is 2 to the 15, okay, so it's quite big. And we are repeating our loop 5 times, so you can also think that we are quite far away from convergence, okay? So it might be that with such a big Hilbert space, we have not, but it seems that indeed we still have good results, okay? So this is to say that we are hoping that this is a good way to go. Okay, thank you, and sorry for the...